Financial Maths Geometric Series Type 4 prizes. So in some questions you can be told that a person has won a prize and the person has two options. They can take the lump sum or they can choose to receive regular fixed payments. So in these questions we're going to look at how would we deal with taking these regular fixed payments. In other words, we're going to be setting up a geometric series. So if we look at page 264 in question 11, we have Mercedes took part in a TV game show and she won the top prize. She's given two options: to receive €1,000 at the end of every month for the next 20 years, or to take a lump sum now. If the AER is 8%, then what is the minimum amount that she should accept as the lump sum? So in other words, what is the equivalent of getting €1,000 at the end of every month for 20 years now, if she's to take the lump sum now? So those €1,000 are received in the future, 20 years into the future. So that means if we want to take a lump sum now, what we have to do is find the sum of all of those €1,000 in the present. In other words, we're going to find the geometric series of the present values. So we would say the lump sum equals the sum of all the present values of the future payments. Okay, so the first thing we should note is that we're given an AER, but yet she's going to receive the payments monthly. So we're going to have to start by changing our rate. So we have P is 100%, which is 1. F is 100% plus the AER, which was 8%. So that's 108%. In other words, 1.08. She's receiving it monthly, so our AER is 1 year, therefore monthly is going to be 12 months in a year. So T will be 12. And we have F is equal to P by 1 plus I to the power of T when we're changing our rate. So we have 1.08 is equal to 1 times 1 plus I to the power of 12. If I get the 12th root of both sides, and I get I on its own, then I'll get my monthly rate to be 0.00643,403. So in other words, my monthly rate would be 0.6434. So let's make it to 4 decimal places. Okay, so now we need to set up our geometric series. So we know that if we're getting our present value, then the prize lump sum is going to be the sum of the present values. And to get present value, it's F over 1 plus I to the power of T. So we're going to write that as a geometric series, where F is going to be our amount, which is €1,000. Our rate, we've just written down there, 0.006434. And then the time, well, we have to look, she's receiving it for the next 20 years, but she's receiving it monthly. So 20 years is going to be 20 times 12, which is 240 months. And the next thing we need to look at is when is she receiving it? So she's receiving it at the end of every month. So if she's receiving it at the end of every month, that means that the first one that she receives, if she receives the first payout from the prize at the end of the month, and we want to know what is it worth today, Then if she receives it at the end of the month, so the 31st of January, and we want to know what is it worth on the 1st of January, then that means we have to discount back that first payment by 1 month. So that'll be 1,000 over 1 plus the interest rate, so 0.006434, and that's to the power of 1. The second 1,000 euro that she would receive, if we want to know what it's worth today, would have to be discounted back by 2 months. The third 1,000 euro that she receives would have to be discounted to today by 3 months, and so on until we get to the last 1,000 euro that she receives. If we want to know what is that worth today, we would have to discount it back 240 months. Okay, so I'm going to take out 1,000 euro as being common, so I can see my geometric series a little bit easier. So I have 1 over 1.006434 plus 1 over 1.006434 squared, all the way down to the last one, which is 240. So this is my geometric series, where A is 1 over 1.006434. Common ratio, 1 over 1.006434. So or is less than 1, so my sum to n terms is going to be A times 1 minus or to the n over 1 minus or. Now, n is my number of compounding periods, so I have 240 compounding periods. So in other words, I have 240 terms in this geometric series. So therefore, the sum of the first 240 terms is going to be A, which is 1 over 1.006434 times 1 minus 1 over 1.006434 to the power of 240, all over 1 minus 1 over 1.006434. So again, putting that into our calculators, making sure we use brackets. So we get 122.0780622, and therefore we can say our lump sum must be 1,000 multiplied by this number. So therefore the minimum lump sum she should receive is 122,078 euro and 6 cents. So in other words, that lump sum is the present value geometric sum of all of those future payments of 1,000 euro at the end of each month. Okay, so on your revision sheet, you're going to try questions 62 and 63. Okay, so the last one, I'm only going to do an example of it. It would be unusual to see something like this. This is where we're going to have sum to infinity. So here we're asked, suppose you expect to receive a payment of 200 euro at the end of each year for an indefinite period of time, then what is the present value of this annuity? So basically we have a payment, so our amount that we're going to receive is 200 euro. The time is indefinite, so infinite. So it's going to be an infinite geometric series that we're setting up here. And we want to know what's the present value of this annuity. So in other words, what is the sum to all of these terms going to amount to? So in other words, we're going to be looking for the sum of the present values. It'll be the geometric sum. So the geometric sum of the present values. So to get our present value, it's going to be P is equal to F over 1 plus I to the power of T. So that future payment that we're receiving is going to be €200. So if we look at the first one, it's received at the end of each year. So if we're receiving it now, today, we're generally talking about, say, January the 1st. And if it's received on 31st of December, then that first payment of €200 that we receive on January the 1st has to be discounted back. So it would be discounted back by 1 year. We don't know what our interest rate is either in this question. So we're going to have 200 divided by 1 plus I, whatever I is, and that first payment received is discounted back 1 year. And discounted back 1 year because it was received at the end of the year. The next one would be 200, and I would need to discount that back 2 years. The next one I would need to discount back 3 years. And that keeps going indefinitely. So therefore what we can see here is we have 200 times 1 over 1 plus I, 1 over 1 plus I squared, and so on. So we can see that it is a geometric sequence where A is 1 over 1 plus I, or is also 1 over 1 plus I, which means then that or has to be a number less than 1. And therefore, because it's a geometric series, or is less than 1, then that means I can get the sum to infinity. In other words, this sequence converges. And our sum to infinity is found by getting A, which is 1 over 1 plus I, divided by 1 minus 1 over 1 plus I. So I'm going to multiply the top and the bottom there by 1 plus I, my lowest common denominator, to get rid of the fraction. So on the top line there, if I multiply 1 plus I by 1 over 1 plus I, then that gives me 1. And on the bottom, if I multiply by 1 plus I get 1 plus I minus 1. And therefore that sum to infinity is 1 over I. And of course then I must multiply that by 200. So if I come over here, so therefore we say our annuity is equal to 200 times 1 over I. In other words, we get 200 over I. So whatever that interest rate is, and that would be in the decimal form. So as I said, it would be an unusual question to get something like that. So there's 1 or 2 in the revision sheet if you want to look at it, but really I think if we're given an indefinite time, all we're doing is getting our sum to infinity.